Hello viewers, welcome to my Facebook and YouTube channel. The previous lecture was about reactive intermediate carbocations. What are carbocations and how are they formed? It was discussed in the previous video. In today's video, we will study about the stability of carbocations, how carbocations are stabilized, what are the groups which make carbocation stable, and what are those groups which make carbocation unstable. As you can see, I have written two statements: electron donating groups which exert plus I, that means positive inductive effect, which donate sigma electrons towards carbon, and plus M effects which donate pi electrons towards the carbon, stabilize the carbocation. They make carbocation stable. You can see here, this carbon, it carries positive charge because it has only 3 covalent bonds. Adjacent to it, suppose we have electron donating group which shows plus I effect or plus M effect. That electron donating group will decrease, neutralize this magnitude of positive charge. It will make the carbocation more stable, less reactive. Similarly, electron withdrawing groups, those which attract the sigma electron or those which attract the pi electron, which show minus I, that means negative inductive effect, and minus M effect, negative mesomeric effect, destabilize. Destabilize means they make carbocation unstable. You can see here, this carbon which carries positive charge, if it is attached to electron withdrawing group, that electron withdrawing group further increases the magnitude of positive charge, so making it unstable and reactive. So as a general rule, we can say electron donating groups stabilize the carbocation and electron withdrawing groups destabilize the carbocation. To make these two statements clear, I will write some carbocations and we will arrange them in decreasing order or in increasing order of their stability. Let us write some carbocations. You can see here, question is, arrange the following carbocations in decreasing order of stability. Option number A is this one, CH2Cl, and this one, it is a primary carbocation. Option number B is CH2F, then again CH2, here positive charge. Both of them are primary carbocations. Then option number C is CH2, then here I will write CH3, and here positive charge. It is also a primary carbocation. This ethyl group CH2CH3, Then option number D is CH3, H, here positive charge. Now we can easily tell which of the four carbocations is most stable and which is the least stable. Let us analyze one by one. Here we have chlorine. Chlorine shows minus I effect. Here we have fluorine. It also shows minus I. But minus I effect of fluorine is stronger than minus I effect of chlorine. So stronger the minus I, less stable is the carbocation. Here we have methyl. This is ethyl group. It shows plus I. Here we have two methyl groups, plus I and plus I effects. So groups which show plus I effect, more the number of groups which show positive inductive effect, more stable will be the carbocation. So now we can easily predict the most stable carbocation. That is option number D, because that positively charged carbon is directly attached to two methyl groups which show positive inductive effect. Alternatively, we can say alkyl groups exert hyperconjugation. That hyperconjugation also stabilizes carbocation. So option number D is the most stable. So I will write the most stable carbocation is D, followed by C. Why C? Because C has ethyl group, CH2, CH3. But plus I effect of ethyl is less than plus I effect of isopropyl. Okay, then these two, option number A and option number B, they are both unstable, because in one we have chlorine and in B option we have fluorine. But fluorine exerts strong minus I, which will make it least stable among these four carbocations. Then C, then we have A, then we have B. This is the correct decreasing order. This is the order. D most stable and B least stable on account of strong minus I effect. Hope the concept is clear. Yes. Let us move ahead. I will write one more point. Carbocations are also stabilized through resonance. Resonance also stabilizes the carbocation, in which positive charge at carbon interacts with adjacent pi bonds. That interaction between positive charge and adjacent pi bonds we call conjugation. which stabilizes the carbocation interaction between positive charge and adjacent pi bond. Let us write one such carbocation where positive charge interacts with adjacent pi bonds. Like this. This is called benzyl carbocation. As I told you in the previous video, benzyl carbocation. First structure, it is second structure will be this pi bond will move out and it will migrate towards carbon and it will eliminate the positive charge of carbon. Like this. Here we will get double bond. Carbon will complete its octet. But positive charge will come at this carbon. It is called orthocarbon with respect to substituent. So this is structure number second. Then structure number third we will get. That is this positive charge at carbon, it will interact with this pi bond, it will move like this. Then third, here we'll get pi bond and pi bond. And positive charge will come at para position. And positive charge will come at para position. This is structure number third. Then one more structure will get. This positive charge will interact with this pi bond like this. Then fourth resonance structure will be like this. So these are called resonance structures of carbocation, or contributing structures, or canonical forms. And at the end we will get the original. It will again move towards the ring and we get the original structure of carbocation. But for some time being, positive charge gets dispersed, delocalized. This dispersal of positive charge helps in stabilization of carbocation. In other words, I can say more the number of such structures which we can write for a carbocation, more will be its stability. Thank you very much.